Let's look at a problem from the book which uses cylindrical coordinates to calculate a volume. The problem, which is number 19, asks us to find the volume of the solid bounded above by the plane z equals 2x and below by the paraboloid z equals 2x squared plus 2y squared. Let's start by getting just a sketch of what this solid looks like. Let's draw the paraboloid first. So we have an upward turned paraboloid. And notice that the origin is the vertex of the paraboloid. So the paraboloid does go through the origin. And cutting through that is the plane z equals 2x. So we have a plane at a slant. Let's say that it looks something like this. Which is cutting down through the paraboloid. So inside the, go up a little bit more. So cutting through the paraboloid, I'll have kind of a circular or oval shape like that. And the plane, this flat part, is going to be the top surface of the solid, and this curved part on the bottom is going to be the bottom part of it. What I'm kind of visualizing is if I took a potato and just sliced through it with a knife, I would have a flat edge like this, which is the sliced edge of the potato, and then I would have the skin down below it like this, and this would be the curved part with the actual skin of the potato on it. Now let's see what the equations are going to look like if we switch them into polar coordinates or cylindrical coordinates. Remember, in cylindrical coordinates, x is our cosine theta, y is our sine theta, and z equals z. Later on, we'll also use the fact that dv is r dr d theta dz. So let's look at the top and the bottom equations. The top surface is the plane, z equals 2x. But in cylindrical coordinates, x is r cosine theta. So that'll be 2r cosine theta. And the bottom surface is given by z equals 2x squared plus 2y squared. But in polar coordinates, x squared plus y squared is equal to r squared. So in polar coordinates, the equation for the paraboloid is z equals 2r squared. So that suggests when I set up my bounds, I would like to put dz on the inside, and then I can integrate from the bottom surface, which is z equals 2r squared, to the top surface, which is z equals 2r cosine theta. So let's actually start setting up the bounds. We know that the volume of a solid is the triple integral over that solid of 1 dv. So what we're saying here is that we want the triple integral of 1 times r dr d theta dz, but I'm going to choose to write the dz first so that I can use the fact that z is going from 2r squared to 2r cosine theta. And now what we need to do is figure out how to set up the bounds for r and theta. So to that end, let's take this and project it down along the z-axis and see what the picture looks like in the xy plane. I'm not going to try to sketch it yet. Let's just find out what the curve of the intersection is. So let's figure out what this black circle-ish or oval-looking thing is when I write it in terms of r and theta. So this is going to be the curve where the paraboloid intersects the plane. So that's where these two surfaces intersect. So I'm just going to set them equal to each other. Since z is 2r cosine theta and z is also 2r squared, that means I can write 2r squared equals 2r cosine theta. Dividing both sides by 2r, I get r equals cosine theta. And you might recall that r equals cosine theta is the equation for a circle centered over on the positive x-axis. Now, if you go through the algebra, you'll find out that the center is at 1/2 and that the radius is also 1/2. Now, I think that what I want to do is place r next, because r is always going to go from the origin out to the circle. So for any of these angles, r will start at r equals 0, and it will stop on the circle, which is r equals cosine theta. So I'm going to start at r equals 0 and stop at r equals cosine theta. And then last of all, I just need to set the bounds for theta. Now remember, theta equals 0 is the x-axis, so going backwards, I'll be starting at negative pi over 2, and I'll continue until I get to positive pi over 2. So for theta, I'm going from negative pi over 2 to positive pi over 2. So now that that's set up, let's start carrying out the integral. Starting on the inside, we first integrate with respect to z, and the integral of r with respect to z is r times z. And that rz is going to be taken from z equals 2r squared to z equals 2r cosine theta. So let's plug in the endpoints and subtract. First, the top endpoint will get 2r squared cosine theta minus, plugging in the bottom endpoint, 2r cubed dr d theta. Next, we integrate with respect to r. The integral of 2r cubed is 2r squared is 2/3 r cubed cosine theta minus 2/4, which is 1/2 r to the 4th. And that's going to go from r equals 0 to r equals cosine theta. We'll plug in the endpoints and subtract. Now we're going from negative pi over 2 to pi over 2 of 2/3 cosine cubed times cosine is cosine to the 4th theta minus 1/2 cosine to the 4th theta minus, notice when I plug in r equals 0, I get 0. Now, 2/3 minus 1/2 is 1/6. So I have 1/6, the integral from negative pi over 2 to pi over 2, cosine to the 4th theta. Now let's observe that cosine to the 4th is an even function, and I'm integrating it from negative pi over 2 to pi over 2. So it's okay for me just to integrate from 0 to pi over 2 and double my answer. So I get 1/3 the integral from 0 to pi over 2 of cosine to the fourth theta. And here I admit I am going to be lazy and let you guys do it. What you need to do next is you're going to need to use the power reducing formula for cosine twice. If you carry that out, you should end up with 1/3 of 3 pi over 16. So we get an answer of pi over 16 when we're